Okay, in section 2.8, what we want to know is, what does f prime say about f, meaning the function? So many of the applications depend on our ability to deduce facts about function f from information concerning its derivatives. Now, because f prime of x represents the slope of the curve y equals f of x at the point of x f of x, it tells us the direction in which the curve proceeds at each point. So it is reasonable to expect that information about f prime of x will provide us with information about the function f of x. Now, in particular, to see how the derivative of f can tell us where a function is increasing or decreasing, we're going to look at the figure that we have right in front of us. Okay, now increasing functions and decreasing functions were talked about in section 1.1. Now, if you take a look at letters A, B, C, and D, now between A and B and between C and D, okay, now the tangent lines have positive slope. And so therefore, f prime of x is greater than 0. Okay, so if you take a look between A and B, okay, you would say that because they have a positive slope, so here there is a positive slope, then we can say that f prime of x is greater than 0. Okay, and the same thing over here between C and D. We can see that it's a positive slope. And so because it's a positive slope, again, we can determine that f prime of x, meaning the derivative of that function, is greater than 0. Now, if you take a look between B and C, the tangent lines have a negative slope. So between B and C, it is a negative slope. And then because we have a negative slope, we can say that the derivative of this function is going to be less than 0. So we're going to have to use this information to answer the preceding questions that we're going to see in this particular section. So it appears that f increases when the derivative, or f prime of x, is positive, and it decreases when the f prime of x, or the derivative, is negative. Okay, now it turns out, we'll see later on, that what we observe for the function graphed in this figure is always true. But we're going to state the general result below here. So now if f prime of x is greater than 0 on an interval, then f is increasing on that interval. If f prime of x is less than 0 on an interval, then f, the function, is decreasing on that interval. Now let's take a look at example number 1. Okay, in example number 1, okay, we're given a graph of f prime. Okay, now what does the function f look like? So in this example, we're given the derivative. So now if it is known that the graph of the derivative f prime of a function is as shown in figure 2, what can we say about the function f? Okay, well, if we observe in figure 2, okay, what do we note? Well, first thing is that we can note that what's happening between f prime of x and where it is negative. Well, it's below the x-axis. And I'll write this in green here. Okay, it is below the x-axis between what interval? It's between what? -1 and 1. So we can say that f prime of x is negative on the interval between -1 and +1. Okay, so what does that tell us? Well, that means that the original function, so that would tell us that the original function, meaning f of x, so the original function f of x must be decreasing on the interval -1 and 1. Okay, now we can take a look at what happens when f prime of x is positive. Well, if you note here, when f prime of x is positive, again, let's take a look at what's happening above the x-axis. Well, over here, okay, it's above the x-axis on the left here, in blue here, and it's above the x-axis over here. So that means that it is positive when x is less than -1 and when x is greater than 1. Okay, so we would say that the original function, f of x, is going to be increasing on the following intervals. Well, it's going to be increasing from -infinity to -1 and 1 to infinity. Okay, and then also let's make note here that what happens at f prime of -1? Well, if you notice, when f prime is -1, the value of the output is equal to 0. And what happens at f prime of +1? Well, that's also equal to 0. So what does that tell us? Well, that's going to tell us that they have what? Horizontal tangents. So f of x has horizontal tangents when x is equal to +1 and -1. All right, now let's take a look at the next question. It says that if it is known that f of 0 is equal to 0, we want to be able to sketch a possible graph of the function. Okay, so what we're going to do is we're going to use this information, part A, and the fact that the graph passes through the origin to sketch a possible graph of that function. Okay, now, again, we want to make sure that we're noticing some of the information from the previous part. Okay, so we know that f prime of 0 is equal to -1. Okay, so if you take a look here again on the original function, at f prime of 0, you have -1. Now, that tells us that we have, drawn the curve y equals f of x passing through the origin with a slope of -1. So this is telling us that we have a curve y is equal to f of x that passes through the origin with a slope of -1. Okay, so I'm going to show that part here in red. So that means over here we can see that this is the first part that we can draw, because we know that we have, again, a slope of -1 and it's passing through the origin. Now we notice also that we have f prime of x, meaning a derivative, is approaching the value of 1 as x is approaching positive and negative infinity. So again, as you can see here, as a derivative, okay, is approaching 1. Okay, so as it's approaching 1, again, x is approaching positive and negative infinity. So from that, we can say that the slope of the curve y equals f of x approaches 1 as x becomes large. Okay, now what I mean by x becoming large, it could either be positive or negative. Okay, now that is why when we draw the graph of f, it's progressively straighter as x is approaching positive or negative infinity. So you can see here what's happening with this graph. Okay, now one important thing that we need to take a look at is we say that the function f in this particular example, okay, has a local maximum at -1 because near x equals -1, the values of f of x are at least as big as the neighboring values. Similarly, okay, f has a local minimum at x equals 1, and that's where the derivative changes from a negative to a positive. So we can see that in a later chapter, in chapter 4, we will develop these observations into a general method for finding optimal values of functions, but it's important to make note of that right now. Okay, now, what does the second derivative now say about the original function? Okay, now let's see how the sign of f, or the second prime, or f double prime of x, affects the appearance of the graph of the original function. Now, we do know that f double prime of x, okay, is equal to f prime. So basically what it's saying here is that we can say that by noting that f double prime of x, the definition would say, okay, well, we have the derivative, and then we're taking the derivative of the first derivative. Okay, so we would know that f double prime of x is positive, okay, when f prime is an increasing function. So we're going to know that f double prime of x, okay, is positive, or I would say greater than 0, when f prime of x is increasing. Now this says that the slopes of the tangent lines of the curve y equals f of x increase from left to right. So this tells us that the slopes increase from left to right. Okay, so if you look at the first figure on the left, which is figure 4, okay, notice the graph of the function. Okay, the slope of this curve becomes progressively larger as x increases. And we observe that as a consequence, the curve is bending upward. Now, because it's bending upward, a curve is called concave upward. So again, these are important words that you're going to need to know so you understand how to answer these questions. So here, again, we can see that the slopes are increasing from left to right. And as it's increasing from left to right, okay, then we determined that when f double prime is greater than 0, the slopes increase, and therefore the function f is concave upward. Okay, now we can also then find out, well, what's happening when the second derivative is negative. So when the second derivative of that function, okay, is less than 0, okay, which means that f prime, meaning the first derivative, now is decreasing. So if it is decreasing, then the slopes will what? They will decrease from left to right. Now, because of that, we would call this concave downward. Okay, so you can see what's happening with these two scenarios. So again, when f The second derivative is greater than 0, the slopes increase and f is concave upward. If the second derivative is less than 0, then the slopes decrease and f is concave downward. So again, here is our next definition. So you want to make note of what is the definition of concave upward and concave downward. Now let's take a look at the next example. Okay, so example, it says here that the figure shows a population growth for Cyprian honeybees raised in an apiary. How does the rate of population increase change over time? And when is this rate highest? And over what intervals is P concave upward or concave downward? Okay, now if we look at the slope of the curve as this function T increases, we see that the rate of increase of population is initially very small, then gets larger until it reaches a maximum at about how many weeks? Well, over here you can see that once it gets to 12 weeks, that's where it's getting its maximum, it's growing faster. Okay, and then it decreases as the population begins to level off. So as the population approaches its maximum value of about 75,000, called the carrying capacity, the rate of increase of the first derivative approaches 0. So the curve appears to be concave upward on what interval and concave downward on what interval? Well, we can see here that from 0 to 12. Okay, so when it hits 12, we're going to say that it is concave upward. Okay, and then the interval, we're going to state that goes from 0 to 12. Okay, and so now from 12 to 18, we would say that this is concave downward. So again, those are your two solutions to when the intervals is concave upward or concave downward. Now, in this example, the population curve changed from concave upward to concave downward at approximately the point of 12 and 38,000. What this point is called is an inflection point. Okay, and we want to know what that means of an inflection point. Now, the inflection point of the curve. Now, the significance of this point is that the rate of population increases, has its maximum value there. So in general, an inflection point is a point where a curve changes its direction of concavity. Now let's take a look at example number 3. Sketching the function of f, given knowledge about f prime and f double prime. Now we want to sketch a possible graph of the function f that satisfies the following conditions. So the first condition is that the first derivative is greater than 0 on the interval from -infinity to 1. And that the first derivative of the function is less than 0 on the interval 1 to infinity. So if we take a look at that, let's tell us about what 1 tells us that the function is increasing from negative infinity to 1. Okay, so if we take a look here, the function is going to increase all the way to 1. All right, and then from 1 to infinity, it's decreasing. Now, in condition 2, if you look at condition 2, it's telling us that f double prime of x is greater than 0 on negative infinity to negative 2 and 2 to infinity. And also, f double prime is less than 0 in between negative 2 and 2. So what that tells us is that it's concave downward on negative 2 and 2 and concave up on negative infinity to negative 2 and 2 to infinity. Now, from the last part, for number 3, the limit as x approaches negative infinity of the function is equal to negative 2. And the limit as x approaches positive infinity of f of x is equal to 0. So what this tells us is that we have horizontal asymptotes. So this tells us that we have horizontal asymptotes. And those horizontal asymptotes is y, which is equal to negative 2, and y, which is equal to 0. So if you notice here, again, here is your horizontal asymptote. And then here is your other horizontal asymptote. So here we have y, which is equal to 0. And then y, which is equal to negative 2. Now let's go back to the first part again. All right, now we know that the first derivative is increasing, okay, which is greater than 0 from negative infinity all the way to 1. Okay, and then it is decreasing from 1 to infinity, but we have to take into account that we have a horizontal asymptote at y is equal to 0 and y is equal to negative 2. And then we also know that it is concave up between negative infinity and negative 2. So it's concave from negative infinity to negative 2. So that means it's approaching this concave up here. Okay, and then where else is it concave up? Well, it's telling us that it's going to be concave up from 2 to infinity. So it's here, it is concave up from 2 to infinity. And then we also know that it's what? Concave down, meaning that here, so from here to here, so from negative 2 to 2, it is concave down. So again, it's important to understand each one of these definitions so you're able to draw and sketch this possible graph. So again, always first, what do? We first draw the horizontal asymptote, which is y is equal to -2. We then draw the graph of the function f approaching this asymptote at the far left, increasing to its maximum point at x is equal to 1, and then decreasing towards the x-axis as x is approaching infinity. So we also make sure that the graph has inflection points when x is equal to -2 and 2, because that's when it changes. So let's go ahead and then make note of the inflection points. So here is an inflection point. So that is at x is equal to -2. And again, that tells you when it's changing. So it's going from concave up to concave down. And then also over here at x equals 2 is an inflection point. Now you also notice that the curve bends. Okay, so when it's bending, okay, it's bending upward for when x is less than -2 and when it's greater than 2, and it bends downward when x is between -2 and 2. All right, now in many problems in mathematics and its applications, okay, we are given a function f, and then we are required to find a function f whose derivative is the function f. Now, if such a function f, capital F, exists, we call it an antiderivative of f. So in other words, an antiderivative of f is a function f such that f prime of x is equal to the function. So in example 1, we sketch an antiderivative f of the function f prime. Okay, let's take a look at example number 4. Okay, so for example number 4, we're sketching an antiderivative. So we're going to let capital F be an antiderivative of the function f, whose graph is shown. Now, where is f increasing or decreasing? Okay, so we want to make note, where is it increasing or decreasing? So if you take a look at the figure here, the function is greater than 0, meaning above 0. So it's above the x-axis for the entire function. So we can say that the function that's given, okay, is going to be greater than 0. Well, it's above the entire x-axis, and that means that it'll be above the x-axis, or the outputs are all going to be above for all x greater than 0. Because you can see here it's going from 0 to positive infinity, so therefore it's above that. Now, since f is an antiderivative of f, we would have f prime, or capital F prime of x, which would be equal to the function f of x and we would say that f prime of x would be positive when x is greater than 0. Okay, so what this means, okay, is our final answer. And that final answer would then tell us that the function f is increasing on what interval? Well, it's going to be increasing all the way from 0 to infinity. Okay, so again, we've answered the question where f is increasing or decreasing. That obviously we're not decreasing in here because again, it's above the x-axis. Now for part B, okay, the question is, where is f concave upward or concave downward? So f is concave upward when the second derivative is greater than 0. So remember that the function f, writing down our definitions from our previous slide, is concave up when the second derivative of that function is greater than 0. Okay, now, but we know that f double prime is equal to f prime of x. So, because the second derivative is equal to the first derivative, then we would say that f is concave upward or concave up when we know that the first derivative according to our definition is greater than 0. And what that means is that's when f is increasing. So if we look at the figure, we see that f is increasing where? Well, it's increasing from 0 to 1. And it's increasing when it's greater than what? 3 here. So where it is increasing, we would then say it is concave up. So it is concave up on the following intervals. From 0 to 1 and 3 to infinity. Now, we also know that for the definition for it to be concave down, f is concave down, for when f or the second derivative, or f double prime, is when the first derivative is less than 0. And that's when the function is decreasing. So where is it concave up? Well, you can see here that between 1 and 3, it is concave down. Excuse me, not up. So concave down. Between 1 and 3. Okay, so now it says, what values of x does f have an inflection point? Now remember, the inflection point is where the concavity changes. So from part B, we know that f changes from concave upward to concave downward at x equals 1. So f has an inflection point there, and then f changes from concave downward to concave upward for when x is equal to 3. So let's take a look here. Here is an inflection point at 1. That's where it's changing, and it's also changing here. So those are the inflection points. Okay, so the inflection points are changing at x is equal to 1 and x is equal to 3. Okay. Now next, it says for part D, it says in sketching the graph of f, okay, we use the information from parts A, B, and C, but for finer details. So we also bear in mind that the meaning of an antiderivative. Now because f prime of x is equal to f of x, meaning that because we know that f prime of x is equal to f of x, okay, the slope of the function y equals f of x at any values of x is going to equal the height of y is equal to f of x. So we would say that the slope of y is equal to f of x at any value of x is equal to the height of the function. Okay, so therefore, what do we know? Well, because we know that f of 0 would equal 0, we would start drawing the graph of f at the given point 0, 1. So again, over here, we know that we have 0, 0 that's given in this function. And we're going to start drawing the graph of f at the given point 0, 1 with a slope of 0. So that means here, let's take a look at this graph. We're going to start at 0, 1. Okay, and then we know that it has a slope of 0, and it's always increasing. So because it's always increasing, it's going to have a concave upward, okay, at the value when x is equal to 1. So from here, once you get to x1, it is concave up. So as it's concave up, we know that once it gets to the value of 3, it is downward, and then it's back up again when x is greater than 3. And if you notice that at the value of f of 3, okay, it is approximately 0.2, so the function has a gentle slope at the second inflection point. But we see that the slope becomes steeper when x is greater than 3. And then for the last question here, it says how many antiderivatives does the function have? Well, the antiderivative of f that we sketched in this figure satisfies f of 0 is equal to 1. So its graph starts at the point 0, 1. But there are many other antiderivatives, okay, whose graphs start at other points on the y-axis. So in fact, f could have infinitely many antiderivatives. So their graphs are obtained from the graph of f by shifting upward or downward of that figure.